Welcome back. What we're going to do in the second part of today's session is to do a little bit more recursive definitions, and then we see. So we've done lists, we've done strings. What next? Trees, absolutely. So to make recursive definitions of a tree is more concrete for you, and perhaps also to give you some extra motivation for working with them, let's look at another exam question. The exam question starts by giving you a definition, a recursive definition of the collection of all binary trees whose nodes store natural numbers. And by now, I think you've seen binary trees in all kinds of sources in the data structures course. This definition somehow should make sense, even more than it did when we saw it at the beginning of the course. Why? Because really you can think of this triple here, of this lambda as being a null pointer, and this triple as saying, okay, that's really a record whose first component holds the value, second component holds a pointer to the left subtree, and the T2 is really a pointer to the right subtree. Even though it didn't look like that, perhaps, in our lecture at the beginning of the course, this is really how one of the possible representations of a binary tree as a data structure. Now, we are particularly concerned in this question with the type of binary tree that we call full. Now, what does this mean? A binary tree is full is every node in it is either a leaf or it has two children. Now, it cannot happen that there is a node which is not a leaf and has, well, a node that has only one child, only one subtree, and the other one is empty. Either they are both empty or they are both not empty. So what I want you to define now is a recursive function full that takes as input a binary tree, and it returns true if and only if the binary tree is full. Is it clear what we need to do? And remember, full means whenever you see a node, it's either a leaf or it has two children. And the node is really a triple of this form. A node is nothing but the root of a subtree. So let's do it. Recap session on binary trees. Well, let's make it singular here. And let's underline it so that I give you time to think. Okay, now you've had all the time in the world to think. So let's start writing. Okay, so what is the base case? An empty tree. Is the empty tree full or not? Remember, full means every node in it should be either a leaf or it has two children. Why not? Absolutely. A tree is not full if you can find a node in it which has one child, exactly one. Well, there is no counterexample. So remember, for every element of the empty set property P holds, there's always true. Why? Because there is no counterexample. Because actually, this is the simplest thing in the world to show. You don't need to work at all. There's nothing bad in the empty set. And to prove a for all statement, You don't need to exhibit something good. The important thing is that there is nothing bad. It would be different if I asked you, if there is a node that has a certain property, then you should return true. In that case, you actually need to find that node. So if the tree is empty, you're in trouble. But if I say every node should have a property, then if the tree is empty, well, that's true. Every node has that property. Vacuously, because there is none. Okay, now we've dealt with the base case. Well, if the tree is non-empty, then it has at least one node. And now, what is it that I want to return? Okay, let's think aloud. And also, everybody at home is probably thinking aloud right now and writing at the same time. Okay, a tree is full is every node, if every node is either a leaf, and the node is a leaf when both subtrees are empty, the left and right subtree are empty. The other possibility is that it has two children. If it's not a leaf, it must have two children, which means that in that case, T1 and T2 should both be different from lambda. But then we will need some recursion, don't we? Because we say every node, so every node in the tree which has this root will also mean every node in T1 and every node in T2 in that case. So okay, one of your colleagues is saying full of T1 and full of T2. Now, let's think aloud. Let me draw a tree. So here's your N, and here you have an empty subtree, and here you have something that say looks like this. That's an end. This thing here is a logical end. Sorry, for once I wrote a symbol. Okay, now, is this tree that I've actually depicted, is it full? It's actually not full. Why? Because if you look at the root here, the root has an empty subtree on the left, but a non-empty subtree on the right, so it has one child. But what would happen if I actually use this definition to figure out whether the tree is full? I would get true. And there is an easy way to figure out that I can never get false, is because there is no clause that says false anywhere. Okay, so we need to actually modify this definition a little bit. It's a little bit too generous. It always returns true, no matter what tree we feed it with. But somehow it points to a correct definition. Okay, so how would you modify this definition? Okay, so we need to check somewhere whether T1 is empty and T2 is not empty, and the other way around. Because these are cases where we want to return false. Okay, so so what are the possibilities here? Okay, when is it that I want to return false for sure? Only one, if he has exactly one child. So if T1 is lambda and T2 is not lambda, or the other way around. T1 is not lambda and T2 is actually lambda. Hmm? So in this case, we want to return false because this means that the root has only one child. There's only one non-empty subtree. Okay, so far so good. Now, if we are not in this situation, what is it that we know? We know that both subtrees are either both empty or both non-empty. And now we can actually write what was suggested before. Okay, so the question is, do we need to write something like true and full T1 and full T2? Well, you can, but by the rules of Boolean logic, true and Boolean expression is just that Boolean expression. You know, it's one of the properties of Boolean logic that true and P is actually P, no matter what P is. So you can write it, but it doesn't add anything. So otherwise, you can actually do this. Otherwise, that is to say, when the other thing does not apply. So basically, this says, if the root is fine, I haven't found any counterexample to my fullness of the tree, then all I need to do is to check the subtrees. And of course, you can optimize this if you really want to by saying, okay, if T1 and T2 are both lambda, I don't really need to do any recursion whatsoever. I just return true straight away. And I only do the recursion if T1 and T2 are non-empty, both of them. But remember, premature optimization is the root of all evils. Never do it. So first get it right, and then you can optimize and get it wrong later. There is no point in having a highly optimized program that doesn't work. It could be really fast, but it doesn't do what it's supposed to be doing, then it's not good. Okay, the question is, why do I call full T1 and full T2 here? Here. Yeah, okay, so this was a wrong definition. So this is the one that we have corrected now. This was the one that we tried before, and you see it had the making of a correct definition. There was something missing. And this something missing was the thing that we've added now. Namely that you should return false somewhere, and this tells you when you should return false. You know, if you're like me, you try something, and very often what I try the first time doesn't quite work. Sometimes it's badly wrong, some other times it's only a little bit wrong, sometimes it can never be fixed. But you see, we made an initial attempt, then I gave you an example where the initial attempt actually would return true, and in fact we figure out that the initial attempt will always return true, which is not what we want, and then we found out how to make it right. Okay, so far so good? Yes. Oh, no, okay. So the question is sort of, these are alternative possibilities. So the question is, do I get false and then I call the function again? Well, no. So you only return false if one of these two checks is positive. That is to say, if my left subtree is empty and my right subtree is not empty, then I know that the tree is not full because it doesn't satisfy the fullness criterion. So in that case, I return false and I stop the recursion. Oh, so the question is, the full function is true at the beginning until I get the false. Well, the full function becomes true or false only when you hit one of the termination cases. And what are the termination cases? They are either this one, I've reached the empty tree, in which case I return true, or I'm at a node where I return false. And this node should be such that it only has one child, either a right child or a left child, but not both. If you hit one of these two cases, then you return true. Note, for instance, that here it could very well be that full T1 is actually a full tree, but full T2 is not. In that case, this call would return true, this call would return false, and the result, the overall result would be false because true and false is false. So for instance, let's actually do the example. Let's look at the example that I wrote before, and let me actually draw the picture here of a tree shaped like the one that I had before. So let me call this tree here T. We would start by calling full on the tree that has 1 at its root. It has lambda, and then it has T here. Now, this is a non-empty tree. We would see what is it that we should return. We should return false, because the left subtree is false, the right subtree is not. Sorry, the left subtree is lambda, the right subtree is not lambda. It's a complex tree. So we return false straight away. Okay. If instead we call the function on a tree that looks like this, now let's call this T1. Let's call this one T2. then what would the result be? We call full on 1 T1 T2. And the result will be true. But let's do the calculations. Okay, so in this case, we look at the definition of the function. This is full applied to a tree of the form root subtrees. Well, we are not in the false case because both subtrees, T1 and T2, are both different from lambda. So we need to call full recursively on both of the subtrees. So this will be equal to full T1 and full T2. Note what we've just written is a Boolean expression. It's a Boolean expression. We are taking the conjunction, the end of the result of calling full on T1 and of calling full on T2. Okay, so what is full of T1? Again, we are looking, T1 is actually 2 lambda lambda, written in our linear notation. Okay, so what is full of T1? Well, again, the false option does not apply. Why? Because it's not the case that one is empty and the other one is not empty of the two subtrees. They are both empty. So this would be full applied to lambda and full applied to lambda. This is the result of calling full T1. Well, the result of calling full on T2 would be exactly the same. And what is this? This is true and true and true and true, which is true. This tree is full. This is not the most optimized program ever, but that's not the aim. The aim is to make you practice recursive thinking. Then you can optimize it later on. Okay, is there, the question is there some practical way of describing that the two trees are different? Well, there is. You could actually write T1 is different from T2, but that's not quite what you want because we are not checking whether they're different. They're checking if one is empty and the other one is not empty. But you could write something like this instead. So you could abbreviate this as false if it's not the case that T1 is empty if and only if T2 is empty. The reason why I'm not writing this is because it's more confusing than just the long-end version that says, okay, if one is empty and the other one is not empty, or the other one, then we should return false. Again, sometimes longer things are easier to understand than shorter ones. Okay, on Piazza, you see one exercise, one of those I think that I posted yesterday, that had to do with a type of tree which is called skew. A skew tree is one where every node is either a leaf or it has exactly one child. So you basically never have two children. You either have none or one. Do you want to help your colleagues to do this on Piazza? So skew means every node has either no child or one. Is the empty tree skew? Well, yeah, because the empty tree is every node in the empty tree has either no child or one, because there are no nodes. Now, what if the tree is non-empty? Okay, so let's go through all the motions here. Sort of, when is it that you want to return false for sure? When both are non-empty. So if the root already has two children, then you found the reason why the tree is not skewed. Namely, already in the root, there is something bad. Okay, so you want to return false straight away if T1 is non-empty and T2 is non-empty. Because you found a node with two children. So the tree is not skewed. Okay? What is the other possibility? The other possibility is that this situation does not apply. So at least one of the two guys, well, okay. So either they are both empty or exactly one of them is non-empty. Okay, so let's do the possibilities. So it's true. Let's do the optimized version now, and let's try to get it right. If T1 and T2 are both empty, then you know the tree is skewed, because the root is a leaf. Okay, what are the other possibilities? T1 is non-empty, and T2 is actually empty. In this case, you want to call the skew function recursively on what? On T1, because he's a non-empty guy. And there is only one possibility now. If T1 is empty and T2 is non-empty, then we call skew recursively on T2. Because to check whether the whole tree is skew amounts to checking the only things that could go wrong are in T2, in the last case. Because, I mean, pictorially, you would have a situation like this. Okay, T1 is empty, so nothing bad there. The only child is the root of T2, and you have T2 down here with its root. Then checking whether the whole tree is skew amounts to checking that T2 is skew. If T2 is skew, then the whole tree is skew. And since It's 13:55 and we are always on time, or try to. I let you do further exercises at your leisure. On Thursday after Easter, we are going to have a recap session, but not on this topic. We are going to have a recap session on linear algebra and whatever else you would like. Yes. Oh, skew means that you can have only one child. So at most one child. Just a second.